Alrighty. There we go. Happy Tuesday again. So we're kind of skipping over chapter 3 here, and I want to spend a little bit of time on what we skipped because we're going to talk about it a lot as we move into array-based sequences, stacks, queues, decks, linked lists, trees, everything from here on out. We're going to be talking about algorithm performance because it's an important topic, and that's one of the things that is more of a science when it comes to programming. Is some things are faster than others. Basically everything we do, we don't really care at this point because we're not doing anything times a million. But if we did something at times a million, I gotta make sure I have chat open here, it would matter. And in data science, we usually deal with large amounts of data. So we're going to be doing things at scale. So performance does matter. I feel a little bad skipping over it. So we're going to talk about it. We need to understand why they perform the way that they do. And then that helps us choose when we're building our solutions, what way we want to store our data. So array-based sequences are a little bit funky to talk about in Python because we have a Python list. Python lists are resizable. They will just allow us to keep adding stuff over and over and over as much as we want, and it works out great. Other languages, their basic array is not as nice. So you have to deal with other sorts of issues. So the book takes you back to a very basic array using some stuff from the Python library that I just mostly skip because, again, for what we're doing, we don't really care. It's good to see how the book does it, but we're just going to use the Python list because it's easier here. But what happens is, this is week 4 already. Oh my goodness, we're in week 4. Start a new project. Nope, I just wanted to close the tip of the day. Week 4 array-based sequences. There it goes. All right, so we start with our list already. So we have, some list is a Python list, and this is nice and flexible. We can start adding stuff to it as much as we want. It will resize itself. In other languages, they start in a fixed size and they can't be changed. And that causes all sorts of trouble later. It's slightly more efficient because you can say, hey, I only really need to store 3 things in this list. So the amount of memory that it uses is only enough to store 3 things. Works out really nice. Python does some stuff behind the scenes, and I honestly just Google it here because I can never remember size of an object in memory. Oh my goodness! Thankfully, it knows how to get this. All right, so I need sys get size of something here. Will tell me what size it is. So if we print sys get size of some list. And we need to import sys. I think we can use our suggestion here. Yeah, import sys. We should be able to see what the size of this object is. 56 something. It's probably bytes. And not the most interesting thing here at the moment. We're going to do a little loop here and start adding stuff to our list and see if that changes. So we'll say, for number in range, let's go to 100 maybe. So we're going to start some list, and then we're going to take some list and we're going to append the number to it. And then we're going to print the size of here. And let's make this a little prettier here. So we'll do a formatted string. So you can say size of the list with, let's actually start at 1, right? Because then we go 1 to 101 with number items is the size of some list. Right, so for whatever this number is, that's how many items are going to be in our list, because we're just going to append a 1, a 2, a 3, a 4, a 5, on and on and on. We'll see what the size of that list is in memory. Here, and we should see that we get some interesting results. So with 1 item, it's size 88. 2 items, still 88. 3 items, still 88. 4 items, still 88. So when Python creates the list, what it's doing is giving us space to store a couple items. I'm guessing 4. That's my best guess right now. Again, the exact numbers aren't all that important for us. But what Python stores when it stores something in the list is a memory address, right? It says, hey, somewhere out in memory is a number somewhere. It doesn't actually store the value for us because everything in Python is saying, hey, there's some location out in memory. So what we get in a fixed location is room for a bunch of memory addresses. Where's the first number stored? Somewhere in memory. Where's the second number stored? Somewhere in memory. Where's the third number stored? Somewhere in memory. Where's the fourth number stored? Somewhere in memory. We don't really care where, because when you go and read memory, that's about the fastest thing you can do in your computer. Right? Memory is really, really, really fast to go and get a value out of memory. It's really quick. Right? Getting something off of disk is much slower. Right? Getting something off the web is even slower than that, because we're sending network requests out and all these sorts of things. So eventually we'll get into doing some fun network requests, and that's really interesting. But for now, we have room to store so many memory addresses. And when we run out of room, what Python has to do is go and get more space. So one of the things we've done before, once you have a list, you can say, hey, I want the value of some list at index something. Really doesn't matter what index we pick, 67. This will go get that value like that in what we'll call constant time, because it says, hey, what's 67 times the size of a memory address? Go read that value out of some list. So what's actually stored in some list is the location in memory where I'm storing other addresses. Kind of like, I think phone book's not really a great example here, but we get a bunch of values in the phone book, right? And then we'll see, who's this name. Do you guys know what phone books are? I'm an old person. I used to sit on them as a kid instead of a booster seat. That's my only memory of phone books. So, but we go look it up. So what Python is doing is giving us a big contiguous block of memory to store all these values, because what it needs to be able to do is for any index, jump to that location and read that value. So indexes give us constant time access to any value by index. We get constant time by index. This idea of constant time means that no matter how many items I have in my list, it still takes the same number of operations. What we skipped over in chapter 3 is this idea of how long things take based on how big they are. So if I give you 100 numbers in a list and I say, tell me what the smallest number is, you have to look at 100 numbers to find the smallest number, right? There's really no other way to go find the smallest number without looking at all of them. So in terms of how big the list is, the bigger the list is, the longer that takes. So we get this idea that this is a linear time. Linear? Is that spelled right? Linear? Probably is. So the more n we have, the longer it takes. Right? So if I have 1,000 items in the list, I have to look at all 1,000. If I have 1,000,000 items, I have to look at 1,000,000 things. So as n gets bigger, the amount of time it takes is linear. It's a nice straight line, right? To do something like calculate the standard deviation, I think we did that last semester as an exercise, right? You have to go get the average of the list, which as far as I know, you have to add them all together and divide by the number. There's probably some math shortcut by math geniuses, but I don't know it. So we'll say that takes n operations, right? So if I have 100 items, I have to go add all 100 together, divide by 100. Now I have the average. Then I can calculate the difference of all of those. I have to go do it again for n items, right? So I've done it once to get the average. I've done it another time to get the difference of the squares, right? So that's really, I've done it 2 times for every n. But because we get to do some funny hand waving, that 2 is a coefficient, right? We get to throw away coefficients, because 2 for every n, or 3 for every n, or 5 for every n, or 10 for every n still grows linearly, right? We haven't got to the point where it's a quadratic growth, right? There's no exponential growth happening. We're just saying, sure, I have to do 5 operations, 6 operations, 7 operations, whatever, so we can throw away coefficients. Come on, spell check. Coefficients. There we go. Hector, my friend, thanks for donating to the Student Scholarship Fund here at the University of Michigan Dearborn College of Engineering and Computer Science. So it's okay. We would still call it linear. Now, we know specifically it's slower than finding the smallest value, but when we're saying how fast is it in terms of n, it's the same. Right? They still grow linearly. Now, if we wanted to do something that for every n value we had to do n more things, that's when we're going to start getting into exponential growth. Right? That is n squared. So we have exponential or n squared time. So for every value, if I have to do something for every other value here, this is going to take me a long time to do this operation, depending on what it happens to be. So we'll look at one of these things that get to be really slow as we go. So in terms of speed, generally constant is best, right? Because no matter how big n is, you still just do x things. If it's a coefficient, we just kind of round it down and say 1. Right? It doesn't really matter. Some constant, right? We don't care too much. Linear, it's not great, but it's not terrible. It's okay. There's one in the middle here we'll look at. If you're familiar with your math, log of n is better than linear, right? When you grow logarithmically, you have that nice little curve or that direction for you folks, right? So it's a slower growth. That's good. You can get linear. You can get log or n log n, which is worse than linear but better than exponential. This sort of thing. Someone just came out with a math paper. I sent it to my friend. They figured out a way to multiply two integers in n log n and not n squared, which blew my mind. I didn't know this was possible. You remember multiplying integers, you take the first value, multiply by every value of the other one, and then take the tens digit, multiply every value of the other one, and then on and on and on. So for every n, you have to do n things. That would be an n squared operation. They figured out a way to do it faster, and blows my mind. Turns out it might not actually be faster though. It's faster for really, really, really big numbers. So is it practical? Probably not. But it's interesting because math is cool like that. By integers n log n. I think it was just came out. No, Texas A&M. I'll have to find the article for you. It was really interesting. I don't see it right now, but yeah, these are older ones. There's something about this Strauss. I don't know. Anyway, so constant time is good. That's the best performance. So what's actually happening when we start adding stuff to our list here? When we append, we don't have constant time appending. We get constant time reads for lists because we have a contiguous block of memory. We just say, hey, jump to this location, read that value. No matter how big it is, it's the same arithmetic. You just multiply by your index, read this value of memory. It's pretty easy. You get one big block, you get to read it, and we find the value. But adding something here, notice these sizes increase, and they're going to stay longer. So from 9 to 16, we're at 184. Right, so it's 1, 2, 3, 4, 5, 6, 7, 8 values we could add without having to change the size here. And then we get to 248, and we get 1, 2, 3, 4, 5, 6, 7, 8. Okay, it's growing a little funny here, but they will get longer as we go. Here's 1, 2, 3, 4, 5, 6, 7, 8, 9. So Python does it really efficiently because really smart people wrote Python. Generally, there's some sort of doubling. So the easiest way for us to think of it is a geometric doubling, and you get some fun effect here. So if we were to build our own list that would expand, and this is what the book does. It's really boring to read. I'm sorry. We'll play with it in lab, and we can graph stuff out, which is kind of fun. We can go back to using pyplot to look at stuff here. But adds are really fast most of the time. So when we think of performance of algorithms, that's the chapter we skipped. We're talking about the speed of things. Generally, we talk about this, they say big O notation. I don't know who came up with it, but sure, that's the Greek letter big O. Okay, so we say, so when we talk about big O, there is best time, there's average time, and there's worst time. Worst case, best case, average case. Most of the time, we don't care about best case because the odds of it being the best case are really low. So I basically ignore that all the time because we don't care how good it can get. We care what it averages, and we care what the worst is, because we can get the worst, and usually we'll get the average. So those are the important ones. So when we look at how long does it take to add something to the list here, well, for these first 4 adds, it was constant. Nothing had to change. We didn't have to make a bigger list. But as soon as we added the 5th item, what had to happen behind the scenes is Python takes some list here and basically saying, hey, I need a new list equals a list of size, size essentially double some list. Python doesn't exactly double. It's got some other smart stuff to it. Don't worry too much about it. But the easy way to go about it is a doubling, and we'll look at the math behind that in a minute. So we basically double it, and then we say for value in some list, actually for index in range of length of some list, we'll take new list at that index equals the sum list at that index. Right? We make a new list double size, and then we have to copy everything from the old list to the new list. Again, we don't have to do this by hand because Python does it for us. But if we were using a different language where arrays were not, if we had fixed size arrays, we'd have to do this copying. So this copy process takes, in terms of how many n items I have, this is linear, right? I have to move n things from this side to this side. So we say it's O of n, right? Linear time, right? Because I have to move these things over. So the worst case is it takes n items, n operations. The average case, though, is most of the time it's constant. It's pretty quick. The best time is still just is one operation. Again, we throw away best most of the time. So appending to a list, the average is constant. So that's O of 1 essentially, right? We get a throwaway coefficients, some constant here, 1, 2, 3, 4. We don't care too much, right? So the average is constant, and the worst case is O of n, right? This idea that we have to copy this linear, copy the things over, right? Copy from old to new array. In best case, we don't care, but it's O of 1, right? Same as average. Now, the reason we can say the average is constant here is we can do a little bit more fancy math. We can essentially call this the amortized average, because even though some of these happen in worst case time and happen in n operations, what we get to do is say, hey, you know what, if we're doubling every time, we essentially get this cool graph here. Let me show you. I think we can just draw it out here. So if you imagine a little graph here, this will be our n items, and this will be our operations, right? To add the, and here's 1, here's 2, 3, on and on and on and on and on, right? So for 1, 2, 3, and 4, right? 1, 2, 3, and 4, it was constant. Took 1. To get to 5, we had to move 5 things. So we had a spike here. The next bunch were constant. Then we had another spike. We had to move those 10 things, right? The next bunch were constant, and then we had to move the next bunch. What you can imagine here is take this line and lay it down. If you amortize it across the next bunch of those calls here, instead of it being a spike, it just lays across this direction. It says, okay, well, let's average it out. So for call 5, 6, 7, 8, 9, it essentially was 2, right? If we just take the standing, this long one, and just lay it down, the next 5 were essentially 2, right, on average. Now, when we take 10 operations to move 10 things, we lay it down the next 10. We have room, right, because we've doubled in size. This is why the geometric doubling works really well for this. We can amortize it and say, well, really, on average, it's 2, which is still constant, right? The first couple are 1, but then everything else is 2 because we've taken the slow one and just averaged it out across the next bunch. It's fancy math, right? And then the book gives actual math for this sort of stuff, which just hurts my head because that's fine. The math is good, and that's the science part of this sort of stuff. But again, it's not that important. We just need to know that it works. So on average, we still can say this is a constant time to add to a list, right? That making sense so far? So to access a value, for adding values, what about removing from a list, right? We can say some list, remove, and we can give it a value. If I say, hey, remove 10. What do you think for worst, average, and again, best, we don't care. So what is the best time if I'm going to remove an item from a list? Is it going to be a constant operation, or is it going to be linear? So what value would be a constant if I have the numbers 1 to 100? What value would be constant to remove? Because if you say remove 100, I have to look at the first one. Are you 100? 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 Until we get to the very end. It took n looks to find 100. Removing the last thing's easy, right? Sure, but removing by value is linear. Because if it's the last item, it took n lookups. If it's the first item, remember what happens in a list when you remove the first item? What happens to everything that comes after it? They all slide down. So it has to move n things back to fill that location. You can't have gaps in a list. So best case, we don't really care, but it's O of n. Average, still O of n. Worst, O of n. It's the same for all of them. Because if you remove something in the middle, you have to do half the lookup, and then you have to shift half the things. Still O of n. If you remove the first thing, n things have to shift. If you remove the last thing, you have to look up n things before you take the last thing out. So removing is pretty bad in terms of performance. The bigger your list is, the slower this is going to be. What about sumList.pop? Remember, pop, you can give an index value. So pop, say 99, the worst, the average, and the best. So this one now, what's the best case for pop? Removing something by index, or popping something by index. Constant, yep, because this is if you remove the very last thing, right, will be constant. You just take it out. It's gone. Nothing has to shift. You get instant lookup to that index to remove the item. You're done. Average time, though, is going to be O of n, right? Because who knows what index it is? You have to shift n things, and even if you have to shift half the things, half of n is still n because we throw away coefficients, right? 0.5n. We throw away the 0.5. Is that? I'm hopeful adding these is useful because this is real conceptual. It's a really dry topic. I'm sorry. It's going to be like that for a little while until we can actually do more fun stuff. And then worst case, still O of n, right? If we take the very first thing, I have to shift all n items down. It's a full n instead of half of n. But again, we throw away coefficients. We don't care, right? We still say it's n. So adding is pretty good. Right? Lookups are really fast, but removing stuff from a list is relatively slow. And we'll look at other data structures that give us better speed. And that's kind of why we study these things, depending on how we want to store our information. Some things are faster and some things are slower. And we'll look at some things are really good at adding, some things are really good at removing, some things are really good at lookups. Right? We got lots of options for these sorts of things on how we want to store our data. And we'll get to some really cool ones at the end. So this is this O of n notation, this algorithm complexity, algorithm performance. Now, this is all terms of time complexity. There's also, to throw another wrench in the wheel, space complexity. So space complexity is talking about how much memory is used to do these things. For lists, it doesn't use any extra memory really, right? We're storing just the values. There's a little bit of extra memory usage because our list is oversized. So at the point in which we've doubled, we now have twice as much memory used as we need. But 2n is still n, right? We throw away the coefficient. So in terms of space complexity or memory usage complexity, right, still n. which is, you have to store n things, you're probably going to need n things. There's some other data structures that do some really funky stuff, which are cool, to get better speed by trading off space. Saying I'm going to use more space to get better speed, which is cool. And memory is pretty cheap in computers. So if you can get better speed by using a little more memory, it's usually a pretty good thing. And that's a pretty good trade because computers have a lot of memory nowadays. Like this laptop, I think has 16 gig. So, I can store a bunch of numbers in here. Okay. So this is all time complexity. And then there's also the space complexity. That's memory. Memory is used. The operations are done, completed, computed. I don't know, whatever you're right, whatever term you want to use for that. Like, how much work is the computer doing? How many times do you have to ask your processor to do something? Okay, so that's for basic lists. Right, we essentially have to double, and we can add stuff. Right, so the book goes through. It uses the C-types array, which is fine. It's all well and good. Again, I just use the basic array or basic list because it's easier, and you can still do all the sort of copying stuff. It doesn't work as efficiently, and we just say that's fine because at no point ever are we going to make our own data structure. Right? The fine folks who wrote Python give us lists and all these other data structures to use. Let's be honest, we're not going to do better. Right? If you want to do better, go get a PhD in computer science. Go research how you can improve the performance by like a very small amount. And I'm glad people do that. Really smart people have done that and make the languages we use faster, which is great. But we're not going to do that. Right? We're just going to use the stuff they already wrote for us. So we just need to know how to use it the right way or use the right tool for the job. And that's why we study this complexity stuff. And by building these by hand, you get a better appreciation for the complexity. That's the best I can say. And I feel like that's probably true. Other than that, we're just copy pasting out of the book because the book gives us how to build these things. It's not very interesting, but here's a good example of building it. So the reading we do in the text and practice is a little bit boring because we're just kind of typing out of the book, but the idea is we want to understand what's happening with each of these steps so that we can understand the performance and implications for that. That's about as fun as it gets, unfortunately. So, here we go. Yeah, so 792 I think had the most. How's that? 15 lines before it had to double again. So eventually, if we add a ton of items here, we could see it'd be a little bit more interesting. It'd stay a little larger. I don't remember exactly how Python computes how it should grow, but smart people figured it out, so it does pretty well. You guys look really bored. I'm sorry. It's not the most interesting topic, and writing it's not much more fun either. Okay, let me go grab. No, that's not it. I've got this over here. I've got the PDF. Make sure we hit everything we need. Oh yeah, here we go. Nope, table of contents. So amortizing sequence types, yeah, writing sequences, multidimensional sets. Yeah, there's not actually a lot in here aside from building it out yourself, which is the boring part here. So I think we've got, what's our assignment due? The 26th. So next week, no, not next week, sorry. On Thursday, right, Project Zero is due. So pretty much we're just going to talk about Project Zero and then the next project. So in terms of array-based sequences, this is the Cliff Note version. You do spend some time, go read the book, right? We have a book for a reason. It's a good reference. He goes into all the details, shows you all the math for that sort of stuff. You can do it when you're bored. I don't know. I hate doing it. I'm sorry. I don't mean to sell it short. It's interesting stuff, but in terms of me sitting up here talking at you, it's really boring. So when we get to lab next week, we're going to go use some of these and then do some performance profiling and see if we can see what's fast and what's slow. So I'll give you some code for graphing stuff, which is really fun. So you can see, hey, how long did it take to do an add? How long did it take to do a remove? This sort of thing. And we can graph it out and actually look at some pictures, which is much more interesting than that. So maybe we could start that now. I guess we can add in a little plot. So let me go to my project. So if you weren't here last semester, right, when you want to go and use plotting, we need to go and add the library. So in our project interpreter, we're going to go add a package. So this is the idea with these virtual environments is that we essentially have a copy of Python here so that when I go add a package, it doesn't get added to the base Python install that my entire computer uses. Now for pyplot, you're probably not going to break anything. It's a pretty solid package and you're going to be okay. But if you're installing all sorts of other interesting packages from who knows where, and packages depend on other packages and you'll just get gazillions of these things, you can break Python if you install bad packages or other stuff might not work like you expect. So generally, these virtual environments that kind of separate out what Python we're using is a good practice. I don't know, Twitter, I find it very interesting. There's all sorts of interesting people posting stuff about data science and Python and stuff. Some guy was talking about he's been doing Python development for 10 years and probably a good twice a month he has to reinstall Python from scratch because he messed it up. It's like, okay, I'm glad it doesn't happen just to me. So it's nice to see that sort of stuff happen. So it should be using my virtual environment here, right? If you're not, it's not the end of the world. It'll be okay. But when you create your project, you can say make a new virtual environment. It's worth a couple extra seconds usually. So when I want to go add a package, I want pyplot. Here's the pyplot package. I'm going to go install that one. And you'll notice this gives me all sorts of other. Oh, come on. Really? Oh, because pip is out of date. That's nice. That's awesome. Can we just try again? Maybe? Nope. Okay. That sucks. Usually this works. So I can go run this if I want. It's really annoying, but sure. Let's go do that. So let me copy this. See if this makes it happy. So pip is the tool that Python uses to install packages. I don't know why it's named the way it is. So let me just open up terminal here and see if that runs. So this will upgrade pip to that latest version that it thinks might solve my problem. We'll see. They might. Okay, tried it. Close it. Let me just close that one more time and try it from scratch. Settings, go to my package for Python interpreter, pyplot, install. Okay, we want a specific version. Specify version. Doesn't have any versions. All right, folks, it is unhappy. This worked last semester. That's the fun thing. Specify version. I'm sorry? I mean, it shouldn't be because I have a new virtual environment. So if you already have it downloaded and it works great, that's awesome. I'm confused why it's not working for me. All right, I mean, we'll run this script, I guess. So let me just copy that and see if it works here. Oh, we already did pip. Oh, hang on, that was pip, and then pip install pyplot. This is a different version. Hang on, I need this version. Pip install pyplot. Nope. If you can give it a version. That's not helpful. 1.5.0. This one, is it already on 6? This one looks like it was 1.5. I broke it, apparently. Okay. Where does it have a... It says matplotlib. Our menu. User guide. Installation. Pip install matplotlib. Why did I not find it? Dash M. All right, that time it worked. That's nuts. I hope it works better for you. I'm sorry, I don't know why this is being obnoxious. See if this works. All right, thinks it did it. Let's go back and see if I picked it up here. Yeah, okay. See, a bunch of packages. I have no idea, I'm sorry. Maybe rebooting would have taken care of it. But now I have pip, or I have matplotlib, and all these other packages that it uses, which is pretty cool. This is 3.6, sure. I mean, we got a bunch of stuff. So it's out here. So now we can go back and take a look at our first plot here. Usually people import specifically calling it PLT. I don't know why, but this is what everyone does. So we'll just steal that. And then NumPy is a really nice tool for doing something with numbers. Again, we'll come to that in a little bit. I don't think we'll need NumPy at the moment. So if we want to track how long something takes here, we need a way to get the time that we started, get the time that we ended, and save that value. So I'm going to have a list of, this will be my, I don't know, times in the list. Now this gets a little funny because we're going to add to this one too, but we're not going to count the time. So if we look up Python, get some time, something like this. This might not be it. Create time minus start time. Okay, this might be it. Might be it. Here, let's try this. So here's time. So we're going to get the time, and then we'll figure out an end time here in a second. So we'll say, I'm going to go start the time. No, not in this one, sorry. This one here. We're going to get this time, and then we're going to figure out the end time. Right? So figure out what time we started, add the number, figure out what time we ended. And then we'll take our times, we'll append the end time minus the start time. Right? Whatever that arithmetic is, that's how many fractions of a second it took to do this. Right? So let me actually move this down because that won't actually work with it. So to be double the size of some list, we want it to be times, I think it's none times the length of some list times 2. I think this is what the book does. Something like this will give me an empty list the right size here, essentially. I just don't want that to crash. We should be able to pop 99. We make that 98 just in case. Because when you have 100 items, the last index was 99, but we removed 10, so we only had 98. So 98 should be the last item here. Anyway, so let's see if this runs. And then when we're done, just to look at it here real quick, we'll print times and see what we have. Oh, look at that. All zeros. Okay, that's not the right precision. We have like a, was it nanotime or something? Python. Here we go, time.ns. Okay, that's nanoseconds. That'll be a little bit better. Time.ns. So nanoseconds, I think, is a millionth of a second. Does that sound right? Something like that. Still zeros. Nope. I think that nanoseconds should be. Is that fast? Really all zeros? Oh, that's obnoxious. What if we make this bigger? We'll get a different number. Still all zeros. It's all zeros. It's fast. There's a way to get this. All right, I won't bore you anymore. I've got other code examples I can copy paste from last time. I'm trying to do it off the top of my head. I thought nanosecond would work. Right. It's all a discussion. I want the code. That's boring. Timing a task. Time clock. I don't know. I'll find it for you later. I'm sorry. We can look at that real quick on Thursday too. But if we can measure how long it actually takes, this is known as runtime analysis. We're analyzing how long it takes to run. It's not great because your computer, if you remember, does a whole bunch of stuff all the time. Right? Just running Windows, there's a bunch of things that are happening behind the scenes, or running your Mac OS. A bunch of stuff has to happen because computers really only do one thing at a time. Maybe 2 or 4, depending on your processor, right? If you have multiple cores, but very limited numbers of things at a time. So in order for your computer to make it look like it does lots of things, it does them very quickly. So it gives each process a little bit of time in the processor. Say, okay, you can execute for a thousandth of a second. And the next task, you can operate for a thousandth of a second, and it just kind of cycles through. So if you look at like Task Manager in Windows, I forget what it is in Mac, you can see your CPU usage for all of these different processes. So I'm using about 40% of my CPU right now, and each one of these tasks essentially is getting a little bit of time, but all of these things are running and get time eventually, right? So analyzing how long it takes a computer to run something while it's running, and this runtime analysis isn't great. It'll give you a ballpark estimate, but every time you run it, it's going to be different because your computer's doing different things every time. So doing the actual math is better, but runtime analysis gives us a good quick feel for it. It's a handy way to just look at it and say, okay, let me see what's happening here. I don't know why this time analysis. Okay, it'll bother me later. I'll fix it later for you. So we'll do some runtime analysis because it's easier to play with, right? And we don't have to do all the math. And we know what the math is. We know these complexities, but we want to be able to see it and kind of graph it out for fun. So we'll look at adding, we'll look at removing, these sort of things, and see how long it takes for our different operations, and it's kind of fun. So you can see that it slows down as we go over time, but why does it keep giving me zeros? Something's not, okay, that's gonna bother me. All right, I think that's about it for today. So if you have more questions on Project Zero, let me know. All right, that's due when class starts on Thursday, because I'm gonna go over the solution to it. We'll spend, probably takes about half an hour to build that one out. It's not too bad. The tests are actually like the slowest part of it, which is okay, because we want to make sure the code works, right? The idea, any code that's worth writing is worth testing. And if we're going to write code, we want to make sure it does what we expect it to do. We don't need to go down every single rabbit hole and try and give it all sorts of bad input, right? But we want to make sure that every time we have an if-else block, we're testing the if block and the else block to get that 100% code coverage. We're eyeballing that. We don't need to pay for the tools that measure it for us. Those are fancy and nice, but we should just be able to estimate and look at it. Okay, did it run here? Did it run here? That sort of stuff as we're planning out our tests. Our code's not that complex. We don't have 50 different things that can happen really. So it shouldn't be too bad. And then we'll take a look at the next project, which will be a project based in recursion. So the lab from today, if you didn't get it done, we've got till next week. That's okay. Shoot me your questions. It'll be similar to that, where we have to do steps and undo steps and find the best possible this sort of thing. So we'll talk about that next project on Thursday as well. Okay. I showed you the basic ugly version in Word, right?
Oh, yes.
So the Visio tool, I don't have it installed. It's on the lab, is a better tool for this, and like it has built-in stuff, which is really neat. But really just like a 3x1 table with class name, attributes, and functions is essentially what we use here. So when you're listing things out, there's a public indicator with the plus sign. There's a minus indicator for private. In Python, we have these conventions, and anything with an underscore is private. So it's a little bit redundant, but that's fine. Right? It's not the end of the world to have additional information here. So I'd say like, was it solve was one of our methods here that took, and then everything says the expected type. It gives a nice visual cue for this. So that was like the X location, or what, row index. And we said it was an integer, right? And then the column index was an integer as well. And then this returns nothing. So we could say returns nothing, a none, if you wanted. With the public function solve, right, that didn't take any arguments, where solve would just say, okay, go find the start and solve from there. Right? This one now, with the latest version in the lab, is going to return a string. It's going to return the shortest possible path here. Right? So this was different from what we did on last week, Tuesday, where solve didn't return anything, and we just printed a bunch of stuff out in solve just to see what was happening. So this kind of cleans it up, makes it a little bit nicer, so that if you want this maze solver to be used in a web application or a mobile application or a desktop application, it doesn't just print stuff to the screen. We can do whatever we want to do with that string representation of it based on how we want to interact with the user. So that's sort of fun stuff. So yeah, you get the pluses and the minuses. So this will be for your class diagrams, right? Class name, attributes, same thing as well. If you have public attributes versus private attributes, pluses and minuses. There's technically the pound sign for protected, but Python doesn't do that, so don't worry about it. Other languages have other sorts of access modifiers and things, so it should be okay. So this is all I need. If you want to do it in Visio, cool, but Word is fine. I've even done it on Notepad before, right? And I draw a silly little ASCII box because it's fun. What do I do? Like a bunch of dashes, and it's just fun to do ASCII art, some art, you know, and then you draw another line. And I don't recommend this approach. It's just, if you're bored, like you can make them, you know, this sort of thing. You don't need fancy tools to do them, is all for that. Yeah, thanks for asking. That's good. Right, because you get points for writing the code, you get points for giving a diagram of the code, and you get points for testing the code, right, for each of the classes. And that breaks down our 15 points there, right? It was 3 points each for each of the classes, right? 1 point for each of them. So if you just give me pictures, you get 5 points, right? Sure, it's up to you. So ideally, you'll get 100%. Right? If you're not at 100%, let me know. Happy to chat with you and figure out where you're stuck. So I won't tell you to go away, I promise. All right, cool. I think we're good. Yeah. Yes, I forgot to do that. I'm sorry. Oh man. Okay. Well, we did classes already. We did recursion. I can start with recursion. Is that okay? Or not too? I don't want to go too far back because that's annoying. They're quick, I promise. They're like 10 questions or less. Is that okay? Thank you. Yeah, it's been a rough semester. I'm sorry. Let me leave myself a note here. Python. Okay. All right. Cool. You folks are awesome. I still don't even have much of a voice. It's been fun. The coffee helps though. Okay, for real now. We're good? Awesome. Take care, everybody.